All right, so this is a little series I'm gonna call YouTube Physics. I just want to watch some cool videos and understand the physics. So I saw a video of this earlier. I was like, yo, this is pretty sick. Let me start it back. That's cool. All right. The reason why I thought that was freaking awesome and why it involves a lot of physics is because you need a certain amount of speed to go through. I don't know if you saw, so let me just play that one little bit right here when he falls. See, he doesn't have enough speed, and gravity pulls him down faster than he's able to stay attached. Okay, and so there's a couple assumptions that we're going to be making in this for this. So we see that the height of this is 7.5. Okay, and so we're actually going to keep all of our units general, and then we'll plug in different things, and we'll see, hey, how high does he have to, how fast does he have to go if he's going to go like double this? All right. So the initial assumption is at the very top. So at the very bottom, he all the energy he has is velocity. Okay, we're gonna call this V1. So the energy at the bottom that he maintains, 1/2 mv squared. Okay. One thing that you're gonna realize is energy has to be conserved. Notice he's not continuing to pedal once he's like riding up or anything like that. Okay. So at the very top, when he's going this way, what he now has stored is a combination of kinetic energy going this way and potential energy that was stored from the height of this. Okay, which we're gonna say height of m. So then this energy total, this one, the first one was purely kinetic energy. The second one has some kinetic energy in it, plus this potential energy. Okay, and if we were to then look at a little bit harder at the very top, in order to maintain contact, he is going to need to have a certain velocity that tracks the centripetal acceleration. That's a fancy thing of just saying that, hey, this acceleration is equal to the v velocity squared over the radius. Okay? And this has to equal gravity. If it's anything less, he's falling down. Gravity's pulling him faster. He's going just like we saw in the video. Okay? And so this is the key part. So if he wants to stay up top at the very height of it, the minimum velocity he needs is gonna be, we're gonna solve for this. So you multiply r over to the other side, you're gonna get rg squared. So you get v is equal to the square root of g times r, where r is the radius of this. So that's actually gonna be half of this, right? Okay. And so now that we have this velocity at the very top, right? That's going to be this 2, okay? And h is actually going to be 2r. So we'll be able to plug this stuff in. So we want to solve for how fast he has to go. So we're looking at this one. We're going to take this equation. We're going to first simplify it. Notice here, it actually doesn't matter his mass. It doesn't. So you can cancel this out on all of these to divide them all. The only reason why it doesn't matter is because you could divide or factor it out here. And so I don't like this 2 being here. We're going to end up, you know, doing this to multiply everything by 2. So we're going to put a 2 here. So the equation we currently have now is v1 squared is equal to v2 squared. I'm just going to plug this in right now. So square root of gr squared plus 2g, and then h, I am going to put 2r. That's what h is. Okay, and so now what we have is v1 squared is equal to gr. So the square root of, if you square the square root of anything, you just get the same thing back. This is going to be 4g gr. And so you add these together, you get 5gr. And so v1 is equal to the square root of 5gr. This is a pretty neat equation. That's very, very clean. So let's see if we were to plug this in, right? What what will you get? So gravity. So we could assume Earth, right? And we're gonna have a little fun, all right? We're gonna have a little fun, all right? Oop. Just gonna put another little picture down here. Okay, we're gonna try different things. Okay, G. Feel free to plug this along. Okay, and play around with different numbers if you like. So the gravitational acceleration is 9.8 r. The radius is half of that, so that's gonna be like 3.75 meters. Okay, and so if we were to plug this in our handy dandy calculator, we'll do it right here. I already had it preloaded. You can see. Boom. It's gonna be 6.6. So we get 6.6 meters. Oh, no. That's what it was at the very top. I'm sorry, that's what you need. Remember, that's this one. This was 6.06 meters per second. This one, there's a 5 in it, and I didn't include it here. So let us see what we get. Ooh. Get 13.5 meters a second. And I know many of y'all are like, what the heck does that mean, dude? Well, I could show you 13.5 meters, right? Is 30 miles an hour. So I'm converting it to miles an hour. Okay. It's equal to 30 miles per hour. So you need to go 30 miles an hour to make this loop. That's freaking nuts, dude. So if we were to put in here like different gravities, to say the gravity of Saturn or something like that, like what would it be? You know, we could also put in different radii. What if it's a tighter circle? What if it's a larger circle? Let's double it up. Let's double up the radius and see if they wanted to go crazy wild, right? What would happen if you had a radius of 7.5 meters? So that means this whole thing would be 15 meters now. All right, because the radius is half of this, remember? So if they were to do this, what would you get? We're changing this. 19.1. So with this one, you'd get a velocity of 19.1 meters per second. All right, let's see what that is in miles an hour. 42.5. Wow. Wow. Did I say 42.5? 42.5 miles per hour. Yo, I don't know if y'all understand how fast these speeds are. What's the fastest speed you could get on a bike? How about that? Let's work it out the other way. Bicycle. So the fastest speed anyone's ever gone on a bike is 183 miles per hour. Well, 183 miles an hour. So like we want to find out what's the biggest loop somebody could go through. 185 miles an hour. 89 miles an hour. Okay. So we're going to convert that into meters a second and then plug it into our equation and actually solve for what the radius would be. Okay. So 185 miles per hour in meters per second. 88.5. This is going to be 88.5 meters a second. That is about, what is it, like 5 times faster than what our guy did right here to do it. So if you were to do that, what kind of, circle could they do it in? So let's work it out. So if I look, it looks like it's going to be r is equal to v squared over 5g, right? Square both sides, and you divide that over. So we're going to plug this in. It's going to be 88.5 divided by 5 times 9.8. 88.5 is squared. 88.5 squared divided by 5 times 9.8. 159.8. 160 basically. You round up. 160. Shee! How? Why is that? That's a lot, isn't it? Yeah, I guess so. Dang, that's freaking huge, man. So 160 meters. That's a whole football field. Woo! They could do that. That's wild. Yeah. So yeah, I just thought that was really neat. So I mean, this cyclist, he had to have been going 30 miles an hour minimum. Minimum. You could go more, and I can explain the physics of that stuff a little bit later. But if you go anything under, you're gonna fall short of the path, just like we saw in the video right here. Once again. That's so clean. All right, but yeah, thanks for joining us. That's the YouTube physics video of the day. Level up, y'all.